Yeah, thanks and welcome also from my side. Thanks for the kind introduction. I've given the distinguished lecturer duty over to Ramiro. So yeah, my name is Matthias Magdowski from Magdeburg, from the Otto von Guericke University. So maybe some words about myself. I was born in 1984, like in the book. You can now calculate yourself how old I am. I'm married. I have 2 children. And I have a background in electrical engineering. So I studied at the Otto von Guericke University of Magdeburg in Germany, yeah, more than 20 years ago. At least when I started, and I did my PhD there. And since about 10 years, I'm also actively volunteering and working as flying faculty lecturer, giving courses at different universities all over Europe. Maybe now in the future also all over the world, because we might have some cooperation with Brazil. And so some words about our university. So this is the building where my office is. This is also the building where our large reverberation chamber is. We also have a reverb chamber in Magdeburg with 4 by 6 by 8 meter size. With first cavity resonance at 30 megahertz, lowest usable frequency around 200 megahertz, something like this. And we also have a nice city. So if you ever want to visit Magdeburg, we would like to welcome you. So this is, we also have a river. It's called Elbe. We have a nice cathedral, and it's also pretty nice there in the summer to walk along the river. And if you don't know where Magdeburg is located, we are in this triangle between Berlin, Hanover, and Dresden, and about, let's say, 1.5 hours by train or by car west of Berlin. And it's not too far away, it was also for me not a long travel to go to the Netherlands. I think it's something like 2 hours by train to go to Hanover, and then 2 more hours to go to Hengelo, and then you're almost here. If you don't know Otto von Guericke, I've also introduced to our PhD candidates on Tuesday. He is the name patron of our university, not the founder of our university, because he lived in 1600 something, and our university is pretty new. It was founded after the Second World War. So our university is only something like 65 years old. But he was also a scientist and a researcher and an engineer, let's say. He was also a mayor of the city and a politician. And he studied the force of air pressure or the force of vacuum, and did a pretty illustrative experiment to show the force. So he, I don't know, who knows the Magdeburg hemispheres experiment? Some people know. So he took 2 large hemispheres about 60 centimeter in diameter and put them together just with a seal. And then he also invented the air pump, pumped the air out of it. So there was nothing inside, just vacuum or very low air pressure. So these 2 hemispheres were pushed together by the force of the external air. And to show how powerful and how strong this pressure is, he did a very illustrative experiment. It's also kind of expensive and dangerous nowadays. So we sometimes repeat it for the anniversary of the university, but not too often. So he took, as you can see here, 8 horses on one side and 8 horses on the other side. And these 16 horses in total were not able to pull the spheres apart that were pushed together by the force of the external air. And then the legend says that a small child came, opened up the valve, the air would flow back into the hemispheres, and they would just fall apart by themselves. So very nice and very demonstrative experiment. You might know this experiment, same experiment, different force, if you have Levi Strauss jeans trousers. So I think he somehow copied or stole the idea from us to show the strength of these trousers. Okay, so if you want to have the slides of this presentation as some organization matter, yes. I also try a recording. Maybe it will work, maybe not. No one ever knows. And if you have questions in between, just raise your arm. Feel free to ask the question. I also have 2 questions in between to you. So search for your cell phone later on to answer these two questions. And so then the motivation for the talk, I mean, here most people have an EMC background, but for maybe the 1 or 2 persons in the room that don't have, so we are dealing with EMC. We are using lots of electronic devices all the time, all the day, and these devices on purpose and sometimes also not on purpose radiate electromagnetic fields, and these fields could disturb the proper function of other devices. So an example would be you have a Wi-Fi router at your home. This creates electromagnetic waves. They could interfere with the TV set. The classical example, I don't have my usually I do some experiment, not with a smartphone, but with a dumb phone. I have it in my backpack, right? The interference, the beep, 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 beep that everyone knows. With a speaker, it's the same kind of problem. And so what we would like to know, or what we would like to show, is there some interference or not? And yeah, how can we quantify this? How can we measure this? So this is the idea of doing radiated emission measurements in terms of electromagnetic compatibility to get some idea, will there be some interference or not? Okay. Then how do we do this? We test instruments and we check the results according to different standards. And we discussed this yesterday and the day before that, what should be written in the standards? Should it just be a recipe so that people know what to do in some EMC laboratory, so that they can apply the standard, do some measurement? Or should the standard also describe all the physics behind and the motivation why we do it in this way? And I don't want to answer this question. The truth is probably somewhere in the center, always in the middle. But the problem with the recipe is usually, that's also what I explain my students in, I don't know, mathematics or physics lectures or electrical engineering lectures. If you don't really understand the recipe, you can also do lots of mistakes. Simple example, if you want to bake a cake and you plan a big party, so you need more cake, so you double the recipe. So you take double the sugar, double the butter, and so on, but you don't need to double the temperature, right? Temperature to bake the cake will be the same, even if you double if you double the recipe. So you need to understand still on which purpose is what in this recipe. And yeah, so from my point of view, don't be this test engineer. If you're a test engineer that just applies the standard, try to understand the physics behind. This is maybe the first takeaway message of my talk here. Okay, so then now if we go a little bit more into technical detail, a very fundamental question is, if we want to quantify this radiated emissions in terms of electromagnetic field of devices, what would be a good measurement? And so what many people do is measure field strength with some antenna in a certain distance. Okay, the motivation there is, okay, if you have a victim for this disturbance, what the victim of the disturbance will see also at some antenna port will be a certain field strength that might cause interference for some radio receiver, for example. What people in the mobile communication world sometimes do, and in the medical engineering world, is to measure power flux density, because this is what will induce some kind of heating effect in human tissue. If you measure specific absorption rate, it's something like you have a certain energy within a certain volume, or you have a power in a certain area, power flux density, something like this. And what you could also measure, probably not a bad idea to do so, as we will see, is to measure total radiated power of devices. What is the overall power that is radiated into all the directions of a certain device? So there are different ways to do it. And the next question is a little bit, on which environment do we do this? We cannot do, as we will see later on, radiated emission measurements, for example, just in a room like this, because there would be lots of ambient other disturbances. So we need to shield ourselves from the environment, but how do we do this environment? Is it really anechoic, like a free space, like a satellite? flowing in an open or flying in an open space. It's probably not what we see here. Yeah, so if we are in a building like this, there's steel reinforced concrete walls, there is lots of metal structure here behind the ceiling, so there are some reflections, and so this is what we in most cases have. And sometimes if you are on a ship, if you are in an aircraft, if you are in some industrial environment, it will be a highly reflective environment with lots of reflections, maybe already a quite high quality factor in the surrounding. So this is, yeah, also some fundamental question a little bit to think about. So then what we can take a look at now in more detail is how to do measurements and what's the idea in semi-anechoic chambers, which are a replication of some classical open area test sites. Then we can take a look at reverb chambers. Then we can try to somehow compare the results between them. And see how well the correlation would be under this in the circumstances. And then a former colleague of mine in Magdeburg, whose name was also Matthias, it's a very popular name in Germany, has performed some measurements with a large metallic box as some unintentional radiator, and we can have a look at some of these results. And finally, I will hopefully also be able to draw some conclusions. So first thing, let's take a look at anechoic chambers. And as said, if we want to do EMC measurements, we want to shield ourselves from the environment, to not measure any ambient noise, any other radio stations, Wi-Fi transmitters, and so on. So we need to have a shielded enclosure, and the shielding acts, or the metallic shielding acts like a mirror for electromagnetic waves. So everything that comes from the outside is mirrored back, which is nice, but everything that you generate on the inside would be also mirrored back from the walls. So imagine you are in a room where are mirrors everywhere and you switch on a flashlight. What will happen? You see lots of light, and you don't know where's the light coming from, where the light will go, because you see lots of reflections and re-reflections of this initial wave. And so this is what would also happen in the shielded room. Okay, we take advantage of this in a reverberation chamber, but usually people do not want to have this, So what you could do with the room with mirrors, like in the Rolling Stones song, take black paint, paint it black. And then the mirror will not reflect anymore. And I mean, light is also just some electromagnetic wave with a very high frequency, very small wavelengths. So our waves in EMC have smaller frequencies, much longer wavelengths. So we need to have this kind of rough surface, but with a much larger surface roughness. And that's why we more or less take these pyramidal absorbers, and they, for electromagnetic waves, act like black paint for light. So yeah, we get a nice environment without any reflections, without any echo. That's why it's called an anechoic chamber. And if the floor is reflecting, then it's called a semi-anechoic chamber, because we have just reflections from half the space. And so we could put our device on a test somewhere, let it radiate, and then with an antenna in a certain distance, measure the emissions. And we could, for example, rotate this and then measure the emission in dependence of the direction. And usually this distance here should be in a way that we do the measurement in our far field conditions. So if we, for example, want to start to measure at 30 megahertz, this distance should be 10 meters. And so this is how this looks like in practice. Also in Magdeburg, we have a large semi-anechoic chamber with this 10-meter measurement distance. As far as I know, we are the only university in Germany that operates a chamber of this size. Yeah, and so a bit difficult to see, but there's a large turntable, and for certain measurements, like immunity tests at higher frequencies, sometimes you decrease this antenna to equipment under test distance to get higher field strengths, and for certain conditions, you might also do not want to have this reflection on the ground, so you can put additional absorbers on the ground. And this is a pretty old picture. So if you find newer pictures, these absorbers here on the back side of the chamber, they will be smaller because we built in a new door so that we can move in bigger vehicles into the chamber for testing, for example, ambulance cars, something like this. And this was in the past pretty difficult to get them into the small door. Okay, so yeah, now coming back to the measurement, what we would like to measure is the maximum radiated field strength in a certain distance, because maximum is the worst case scenario that could interfere with some radio receiver as a victim of disturbance in a certain distance. And we would like to get this maximum over all the directions, all polarizations, as a function of frequency. Still, this would take quite a time. So what we actually measure is the field at a certain distance, but the maximum over these angles that we measure. So we somehow undersample there. And if at least you have a floor standing equipment, you put it into this anechoic chamber and you rotate the turntable, you more or less just measure one spherical cut. If the equipment under test radiates to the top or radiates to the bottom, and then it will be reflected by the ground plane going back to the top again, no one will measure it. The rationale behind this is, okay, in former times, propagation mainly took part in a horizontal direction, and you did not had so many devices that would be stacked on top of each other, but okay, above me here in this room, there's nothing, but at least if EOP would radiate or has something that would radiate, there's a projector directly above him. So in office environments, in household environments, industrial environments, it will not be uncommon that there's something on the top, and you do never really measure this radiation in a semi-anechoic chamber. Except for you somehow switch tilt the device, I don't know. Okay, so then let's go for reverberation chambers. So I thought to delete this question because I thought there will be, but still I let it in. So please, I'm interested about the results. So I do not assume that everyone answers the first answer because after the two talks before, you should have heard of reverberation chambers before. And but yeah, maybe there are some people that have never used it. There should be some people that are aware of the fundamentals, and I would be interested in how many people answer the number 5, because it should be at least, I don't know, 5, 6, 7 people. Okay. And yeah, and we also have some measurement uncertainty and some bias in, in this survey, because some people forgot their phone. And I still see some phones pointing at me, so I will wait some more time to take a look at the results.
VPN is not allowed.
VPN is not allowed? But does it work for someone? Yeah, okay. Okay. Okay, so then let's switch over and take a look at the results. Okay, and as expected, there are 0 votes for I've never heard of a reverb chamber before. And the most common answer is that I've already conducted some experiments, and as I assumed there are 5 people that say I run my own chamber and I have some greater experience there. Okay, so thank you for this. So yeah, we've heard some introduction into reverb chambers, but maybe my usual brief introduction that I already give. So once again, we want to do radiated EMC measurements. We need to shield ourselves from the environment. So we take these metallic walls. Metallic walls will act like a mirror. And so now if we, for example, have our device on a test here, let it radiate. It will radiate, and let's say it will radiate in this direction. So then the wave will be reflected, and it will go here, it will be reflected again, it will go to this direction, it will be reflected again, and so on and so on. So we get lots of these reflections and re-reflections, and we get traveling waves traveling in opposite directions and interfering with each other. So we can get positive and negative interference, and we get standing waves. And standing waves means that there are points in space where the field strength can be pretty high, which are the antinodes of the standing wave pattern. And there can be points in space where the field strength is very low because there's this destructive interference, which are the nodes of the standing wave pattern. And so now, for example, if you would like to do an immunity test and test a device for susceptibility, you will need to take the device on a test and move it around and find some position where you have the highest field strength. But usually you don't want to move the equipment on a test around because it might be heavy, there might be cables attached and so on, and you don't want to go in there to move it around. So the idea is a little bit, if the prophet cannot go to the mountain needs to go to the prophet. You let the device on a test stay in place and you try to move the field around. And these standing waves in electromagnetics are called modes. And so we would like to change these modes. So we take a large metallic object, and this metallic object, if we move it, we change the reflection of the waves, we change the standing wave pattern, we change these modes, we steer the modes. That's why we call this a mode steerer, and the whole thing a mode steered chamber. Or because we have lots of echo, we have lots of reverb, we could also call it a reverberation chamber. So that's the basic idea. And then you might have one or two antennas to transmit field, to receive field, and so on. So this is the quite popular and iconic photo of the chamber in Magdeburg that was taken, I don't know, also probably more than 20 years ago. The motorcycle was actually never tested. It was a motorcycle of a student that was just put into the chamber to make the photo look nice. And it somehow worked out because it's like the photo for our NEPIT project. It's, if you search the English Wikipedia for electromagnetic reverberation chambers, you will also find the photograph there. I've, in the presentation on Wednesday from Makoto Hara, I think I've also seen pictures with a motorcycle from Kawasaki inside the chamber. So good use of our idea. And yeah, you can see there's an antenna here, there's a shielded camera, and there's also this large mode steerer. And we replaced this 2-3 years ago with another model because this turned out to be not very efficient because it's large, but it's not really asymmetric. It's if you look onto this steerer with this metallic plates, let's say with the vision of a low frequency, high wavelength field, it looks like some irregular shaped cylinder. And if you rotate the cylinder, nothing really happens, nothing really changes. That's why the steerer at low frequencies is not very good in changing the field pattern. So yeah, then this is a question that someone asked me maybe also 10-15 years ago at a conference. Hey, Matthias, you do measurements in these reverb chambers, and as far as I understood, it's some high Q resonant cavity, as also Walter explained to us. And if you hit a resonance of this chamber, don't you get then some incredibly high field strength inside the chamber? And so, yeah, this question I will give to you. So this is the second survey for today. It's a different page, so you need to scan once again. So the question is, what happens if the frequency of the excitation coincides with some eigenfrequency of this chamber, a resonant frequency of the chamber? And the answers, or the answer options are, okay, there will be some incredibly high field strengths, or this is not possible because the frequencies will never exactly match, or this is nothing spectacular, this is the usual operation of a reverb chamber, or there will be a large power reflected back to the power amplifier from the transmitting antenna. And there's still one cell phone looking at me, so I will wait a couple of more seconds. And I think most people have casted their vote, so I will take a look at the results. And yeah, so as expected, I'm talking to a very educated audience. So most of the people have the right answer. Nothing spectacular will happen. This is the usual operation of the reverb chamber. And we not always excite one of these resonances. If the chamber works well, we excite several of these resonances at the very same time because there is some modal overlap. And this is the way how it works. Okay, excellent. So yeah, then the question is how to steer the field, how to change this electromagnetic boundary conditions. We have seen some of these ways in the talks before. Have a rotating mode steerer, move antenna positions around. If you just want to do immunity testing and not emission testing, you can also do this frequency steering because the bandwidth of the chamber is usually much smaller than, let's say, the bandwidth of your device on a test that you would like to test. And there's, of course, also this idea of moving the walls. The very iconic photograph of the first work prototype, a nice video that exists there with these neon tubes where you could also see the field pattern on the inside. And I think this picture is cut here a little bit, but these are the facilities that we very nicely visited yesterday at Thales. So the building where some radar was installed inside the building, and then the portable reverb was put on the outside to measure the electromagnetic compatibility of this radar. So I think it's not really on a chip, it's at some building, right? But it's a chip radar. Okay, and so this is also a picture that we have seen in the talk before with the moving wall steerer. There are many options and ideas to steer the field at the end. So the two important properties that then we would like to have is homogeneity. So the field distribution and the field behavior should not depend on the position, and isotropy. The behavior of the field should not depend on the orientation. And this will, of course, only be valid in a certain distance to the walls because the walls are metallic walls. The boundary condition is that on the surface of the walls, the tangential electric field should be 0. The normal magnetic field component should be 0. So if you want to achieve these conditions, you need to have a certain distance to the walls. And usually it's assumed that if it's greater than, let's say, a quarter of the wavelengths, then these conditions are fulfilled or are satisfied. At the end, this reverberation chamber, as discussed before, is nothing more than a large microwave oven. But for immunity test, we don't cook chicken, we cook electronic chicken. And there's no real analogy for the emission measurements, but it's still pretty the same. So every one of us, I assume, has a small reverberation chamber at home. So then coming back to the EMC measurement, what we would like to measure is the total radiated power. So because it does not really matter in which direction something will radiate, it will be always reflected back from the walls, and it will always be received, or it will always propagate to our receiving antenna. So for all frequencies, we can try to measure this total radiated power. And then what we actually measure is the total radiated power falsified by this intrinsic field uncertainty or statistical field uncertainty, the remaining inhomogeneity, the remaining anisotropy of the field. And this limited sample size that was just nicely discussed before. So how many of these samples are statistically uncorrelated, how many of these boundary conditions are statistically uncorrelated. But the problem is, for this total radiated power, there are not so many limit lines. So if we want to compare this with the standard limit, the limit is given in terms of maximum field strength in a certain distance. So if we want to apply these reverberation chamber measurements, we would need to convert the total radiated power to field strength in a certain distance. So that's the idea of the next section. So what we need for this, and what is the most important parameter, is the so-called electrical size of an object. So let's assume we have some equipment under test. We put some sphere around this, the smallest sphere that would enclose the object, and call the radius of the sphere A. And then we have the wave number that depends on frequency and velocity of propagation, and k times a is the so-called electrical size. And I mean, then there's the question, if cables are attached to your object, will these cables count into this radius or not, and to which extent? But let's say we somehow have some rule for this. So yeah, now we can take a look at this for different values of this k times a, this electrical size. And the first thing is, if this k times a is much smaller than 1, we would call this electrically small objects. And every electrically small object, no matter how complex it is, will always radiate like a dipole. And the dipole shaped radiation pattern looks like a donut. So it's pretty easy to find the maximum emission of this donut. If you rotate the donut in 4 different orientations, you will always find a maximum of the radiation of this donut. Problem is, if we go to higher frequencies, if this k times a gets larger than 1, and so here I can show a video that was produced by Magnus Höjer of the Swedish Defense Research Organization a couple of years ago. And so they measured the emission of like a cabinet-sized object, something like 2 meters in size, for different frequencies. And just a spherical cut, and you can see that for low frequencies, or for lower frequencies, these radiation lobes are pretty wide. Still, it's difficult to guess or to assume in which direction the maximum radiation will happen. So the maximum is moving around somewhere, and if I don't know, can I stop? Yeah. So if I would stop at this position, if you would, for example, just measure 4 directions, this one, this one, this one, this one, you would measure almost no radiation at all. Still, there is a very high lobe going in this direction, this direction. And so even if you would then go down to 30 degree step size, okay, you would measure this, but you would not measure this radiation lobe. And so if we go to higher frequencies, I will skip forward to, I don't know, a 10 gigahertz, then you can see that these radiation lobes get narrower and narrower. It almost looks like a hedgehog, pencil-like radiation beams. And it's very challenging to find this maximum radiation because this, depending on frequency, moves around and it can be pretty narrow. So you would need to measure lots and lots and lots of steps, degrees of the turntable to get the maximum emission. And it takes quite a time, right? So the higher the frequency, the bigger the problem, because the longer you would need to wait and sample to get your maximum emission. And this can be costly. So now there is one way to somehow this was for 10 gigahertz. And if we would, I mean, in the video, we could go up to, I think the video is measured up to 20. Yeah, for 40 gigahertz, I would say this is pretty nonsense to measure, to try to measure maximum field strengths under these conditions. Because as you can see, you would need to sample in sub-degree steps to get the maximum emission. It depends. It depends on the electrical size of the object. If this k times a gets much larger than 1, it does not make any sense at all to continue with these measurements. Yeah. So there are many approaches to still try to do a conversion or correlation between total radiated power and maximum field strength. And at the end, you can burn it down everything to directivity. You need to estimate the directivity of your equipment under test. And this directivity is defined in terms of what is the maximum radiated power flux density divided by the average power flux density in all directions. And for electrically small objects like a dipole, it's known, and for electrically large objects, it's a question. And So there are some standards like the IEC 61000-4-20 for the GTEM cell. And there they just assumed a maximum directivity of 3, which works for many cases. I remember that I discussed this issue with Perry Wilson, who was the convener of this group at this time, and he said, we were not good, we were lucky with this assumption. And yeah, so for many cases it works. So if we know the directivity, we can convert total radiated power to maximum field strength for the fully anechoic room. And there you just need to have free space wave impedance and measurement distance. And in this case, there is no ground plane, no reflection. If we want to take into account the ground plane and the reflection, we need some additional geometry factor. And this geometry factor takes into account the superposition of the direct path between the EUT and the antenna and the one reflection at the ground that happens in the semi-anechoic chamber. So this would be for the fully anechoic room, and this is for the semi-anechoic chamber. And yeah, so these are all known geometrical parameters. You just need to have this directivity. And so then Hans-Georg Krauthäuser, about 15 years ago, thought about this based on some other ideas. And there's a nice statistical model. You take a sphere, you distribute sources on the sphere, and the size of the sphere corresponds to the size of your object, and then you do a statistical simulation with different positions of these sources to estimate the directivity. And yeah, here's written this paper. It's, I don't know, maybe cited 20, 30 times. Unfortunately, it never really made the way into standards. So what I did some years ago, I took his Python scripts to do the simulation, converted these Python scripts into MATLAB scripts, and MATLAB is the same as Octave, and I put them on some Octave online bucket. So if you later on might want to click on these links, you can do these simulations yourself. So there's one script that does conversion or correlation between the semi-anechoic chamber and the RC, and what we see here is directly this conversion correlation factor, maximum emitted field strength divided by total radiated power for a certain size of the object for a certain measurement distance. And for example, the dips here, or this frequency dependence in the curve, this is due to the reflection at the ground. But we can see that for small frequencies, it's pretty constant, and for higher frequencies, it's going up because the directivity, the estimated directivity, increases. And you can see that there's a certain spread. So there's the average, the median, and the 5th and 95th percentile. So 90% of the values for typical unintentional radiators should be in this range. So the uncertainty here is due to the uncertainty of the equipment under test of the radiation pattern. And you could do this for other parameters, for example, for fully anechoic rooms. And for this fully anechoic room, yeah, there is no ground reflection, so you could scale this with respect to frequency. You could also just scale it with respect to the electrical size of the object. And we can see, okay, if the electrical size is small, it stays constant. If the electrical size increases, its directivity is growing with frequency. So the question at the end is a little bit, if you go to semi-anechoic chambers or fully anechoic rooms, you know the environment pretty well. The environment is deterministic, no problem, but your equipment under test introduces a big uncertainty because no one knows the radiation pattern and the directivity of the equipment under test and how many turntable steps you would need to measure. And so your EUT behavior is random and you don't know about this randomness, or it's pretty complicated to estimate the randomness, the uncertainty introduced by the radiator. Still, people like this because the environment is deterministic. And I mean, if you go to low frequencies, small EUTs, it's no problem because everything radiates like a dipole. So if we go to reverb chambers, the environment is random We have this intrinsic field uncertainty that was discussed before, but the behavior of our EUT is totally deterministic because we don't care about radiation pattern, we don't care about directivity, and we don't have a problem if we go to high frequencies, we don't have a problem if we go to low frequencies. The behavior of the EUT is deterministic. The only randomness is introduced by the environment, and we can control this randomness by measuring more or less samples, for example. Investing more time, we can measure more stereo positions, we get a lower uncertainty. So we have done this in Magdeburg. I said a colleague with the same first name as me has done this, Matthias Hörte. But he's written with 2 T. My parents could not afford the second T. So he has taken a large metallic object, put it in the reverb chamber, put it into the semi-anechoic chamber, and measured total radiated power here, maximum field strength in a certain distance here, and tried to do the conversion. And the conversion here is done assuming that the directivity is 1. So the difference between the 2 curves is the directivity of the object. And then you can see, okay, that uncertainty in the semi-anechoic chamber, yeah, there is some fluctuation over frequency, but it's pretty small. In the reverb, there's much more fluctuation over frequency because we have this intrinsic field uncertainty. And yeah, so here you can see that the difference between the 2 curves is not really increasing with frequency. Because in a semi-anechoic chamber, this was only done with 90-degree steps. Then you undersample, you don't get the maximum anymore. So what he also did is do measurements with different step sizes of the turntable in a semi-anechoic chamber. And so you can see if you go from 90-degree steps to 10-degree steps, the difference can be pretty high. And if you would go to 5-degree steps or 2-degree steps or 1-degree steps, it would probably be even higher, especially for high frequencies. And that's exactly the problem. So in summary, we want to do robust EMC tests, repeatable, nice, robust EMC tests. And in a semi-anechoic chamber, it's just not possible because this IUT directivity will hold us back. No one knows about the radiation pattern of his or her IUT and the directivity. Yeah, so because of this, at higher frequencies for electrically large objects, it's simply not possible. It's not very feasible to do so. So then we have this reverb chambers. It's very nice there. So we can measure emissions in reverb chambers. We can do it at high frequencies, small wavelengths, no problem. Measure total radiated power, very nice. But there's no standard for there are no limit lines for this. So what we would need desperately is limit lines for total radiated power, because then it's much easier for comparison. No one would need to do this conversion anymore. So yeah, from these 3 aspects, we want to do robust measurements in terms of it should not matter where we exactly place the equipment under test, how are cables oriented, and so on. This is what I mean with robustness. We want to do it fast, and we want to do it precise in terms of what we discussed before. People would like to trust it in terms of repeatability. If I do the very same measurement in the very same conditions, I should get the very same result before. So robust and fast, this is what reverbs can do, no problem. Fast and precise in terms of repeatability, or let's start here first. Robust and precise in this term, this is what the semi-anechoic chamber would do for you if you would really do the full sampling, measure many steps of the turntable, but then unfortunately it's not fast anymore. And so yeah, if we go to semi-anechoic chambers, do what we do now, measure emissions, but with undersampling, then it's fast and precise, but it's not really robust anymore, because it might depend on if your cable goes to the side first and then goes down, or the cable goes down first directly, something like this. So all good things. The perfect test environment that combines all 3 aspects in the center, unfortunately, does not exist. But still, I would say the factor that you can neglect the most is this precise in terms of repeatability. We want to have robust tests, and for economic reasons, we want to do them fast. So for electrically large objects, for high frequencies, the way to go is the reverberation chamber. Everything else just does not make sense. This is, let's say, the main conclusion of my talk. Thank you.
Can you repeat your last sentence? Any way to go?
For electrically large objects, to measure emissions robust and fast, the reverberation chamber is the only way to go. Everything else just does not make sense.